Hello. Today in Math Club at Kuwait University, we will have a lecture about Elastica and Splines, presented by Dr. Michael Johnson. Dr. Michael is one of the members in research groups in the math department about computational mathematics and analysis and approximation theory. So he will present some of the results about splines and elasticas, especially James Bernoulli's equations, and some of the applications and the research about these topics from the late 60s up to like in the present years. So I will let you right now with Dr. Michael.
Thank you, Omar, for the introduction. I'm really delighted to be here and happy to see the Math Club active. So, let me get to the start here. So the title of the talk is Elastica and Elastic Splines. So afterwards, you'll know what both of those things are, inshallah. Here's a quick outline. So I think many of you haven't been introduced to curvature in Calculus 2. So I'll have to do that at the very beginning because a lot of what comes afterwards involves curvature. This is applied to a curve. And then we'll go back through history. So we'll start with James Bernoulli's rectangular elastica in 1694. Then that's a very special case of elastica. Then general elastica was Euler's in 1750. Then the draftsman spline, that's an actual thing, not mathematics. And then stable nonlinear splines, this is General Motors in 1964. Then we start looking at the research. So there's Lee and Forsyth, they give some necessary condition. Goulomb gives a proof of existence. And then finally, if we have time, I'll mention some of the results, some of the contributions in Kuwait University. Okay, so let's get started on the definition of curvature. So it's denoted by kappa. And if you have a point on a curve, then kappa is defined to be 1 over the radius, so 1 over r, and it's the radius of the osculating circle. So let's see if I can demonstrate that. So here's a curve, and there are 2 points on the curve. You can see this pointer, right? There's 1 point here and 1 point there. And we want to discuss how much the curve is curving at those 2 points. Would you agree that it's curving more at 1 point rather than the other? Yeah, okay. So this one over here, it's curving more. So there's something called the osculating circle. You know tangent line, right? So if we're talking about this point, you could easily draw the tangent line. The osculating circle is a circle that is tangent at that point. So this circle is tangent at that point, right? But it's not the osculating circle. What you want to do is make the radius of the circle so that you get like the best approximation to the curvature there at that point. So I think that would be about it. And over here, let's see, that's too far, right? So I need to come in, maybe here. Okay, so those are the osculating circles at those points. And now, curvature is 1 over the radius, right? So the small circle, the radius is small, so 1 over the radius is big. Curvature will be large. And with the other point where they have the big circle, 1 over the radius will be small. So the curvature is small. So that's how curvature is defined. Now, if you have a parametric curve, and in this talk we're always working with parametric curves. So if you have a smooth parametric curve, x equals x of t, y equals y of t, there's a formula for the curvature. It involves first derivatives and second derivatives of the components, x of t and y of t. It's not terribly important what that formula is, but there is one. Okay, now, this was the problem, the original problem of Elastica posed by James Bernoulli in 1690. I think he posed the problem in 1690, and he gave his solution in 1694. And this is the actual figure that when he posed the problem, this was his figure. So what's going on is that there's an elastic rod. You can think of it as a fishing rod, but it would have to be a uniform diameter. And it starts off here vertical, so maybe it's been hammered into the ground, and then there's a weight hanging on it, and the weight is chosen so that this turn is 90 degrees. And then that angle right there is 90 degrees. And that's very important that the angle be 90 degrees. This is somehow the simplest case of Elastica. And it's called rectangular Elastica because of that. So James Bernoulli analyzed it, and he came up with this equation. dy equals x squared dx divided by square root of a to the 4 minus x to the 4. Now in those days, you're probably wondering, why doesn't he write dy dx equals that thing? So in those days, dx and dy were infinitesimals. They didn't have the limit. Cauchy defined the limit. Cauchy died in 1850 or something. So the limit must have been defined in the early 1800s. So this is long before the concept of the limit, and this is how they wrote things, using infinitesimals. Now I'll show you his solution of how he comes to this equation. I have another little thing here. Okay, so this is his sketch. Very complicated, huh? We don't do that anymore. And where is the elastic curve that... You can see it here. It says curva elastica. It's right there. Now, I've got a elastic curve here. You can think of this red line as an elastic rod. And at the bottom there, it's fixed, right here at the bottom. So it's fixed to come up vertical. And then I'm applying a force that's perpendicular at this point as I move it. That force is always perpendicular. And if I put it here, this is where it's supposed to go. Can you see that it doesn't quite line up with James Bernoulli's sketch? Okay, he did pretty good. If I move this point over here a little bit, it starts to line up better. So I think that this vertical axis here, he should have drawn it a little further to the right, and then it would have been correct. All right, so that equation, you can, Bernoulli's equation, you can realize that it's actually a periodic function, although he was only doing one little arch of it, but it extends periodically, and you can write it as a parametric equation. So it can be written like this. So x is going to be an integral, and y is sine t. And this is one of these functions that you can't integrate. Actually, James Bernoulli was very disappointed. He didn't feel like he had completely solved the problem because he wasn't able to do the integral. But nobody can do the integral. It's not his fault. So this integral is, you can't avoid it. Now, I want to show you how this equation is derived. So I've rotated the setup a little bit to better suit my screen here. So what's happening now is the rod is fixed here, and it's to be horizontal. And then we're applying a force down here so that this is going to be a 90-degree turn. And that force is perpendicular to the curve, to the rod at that point. Okay, so how does Bernoulli come about his equation? Well, I think you would all know Hooke's law, right? So if you have a spring, and this is its nominal length, and if you extend it to be longer than that, you pull it down by some measure x, then what's the magnitude of the force?
Minus
Okay, force equals, I pointed it down, so, okay, minus, yeah, the magnitude is k times x. So we have something like Hooke's law, or Bernoulli had something like Hooke's law when you bend a rod. When you bend a rod, it's kind of like a spring, but not a curly spring, a different type of spring. And his rule was that, well, all right, so so here x is the extension. So we'll say that the magnitude of the torque at a point equals a constant times the force, times the curvature at the point. So we can look at this point. So here's a point xy on the curve. And you can imagine, so I painted it blue on one side and red on the other side. If you think about the forces acting on that blue point, but the red side of it, it's coming from, the blue side of the rod is acting on that point. And it's, because of equilibrium, it's applying a force to counteract F. And also it has to apply what? A torque, right, to keep it from spinning. How much is the torque? Well, we can compute it because the formula for torque, for the magnitude, I don't care about the sign. The formula for the magnitude of the torque is the magnitude of the force times the orthogonal distance from the point to the line through the force vector. So that orthogonal distance is y, and so what that means is curvature equals a constant times y. All right, so if we come back to these parametric equations, I wonder, can we confirm that this curve satisfies that? Curvature equals a constant times y. So let's give it a try. By the way, this is a seminar, so you all are at liberty to interrupt and ask questions. Don't be shy. Okay, so x equals, as given, what's going to be x prime of t?
Sine squared of t.
Okay, sine squared t divided by this one. Sine squared t. And y prime, cosine t. Now, I can do y double prime minus sine t. And x double prime gives me nightmares. So what are we going to do? We'll say it's 2 sine t cosine t times that square root thing, right? Or we could just leave it over there. And then minus. Then it'll be sine squared t times t. And it's this thing to the minus 1/2. So we'll have minus 1/2, this thing, to the minus 3/2. And then we have to multiply by the derivative inside, which is 2 sine t cosine t. So the minuses cancel. And x double prime of t equals 2 sine t cosine t divided by the square root 1 plus sine squared t plus the 2 also cancels there. So it's sine cubed t cosine t divided by this thing to the 3/2. Okay, now we need our formula for the curvature. So we have to take x prime times y double prime. There's also the denominator, right? Let's do the numerator. So the numerator, absolute value of minus sine cubed over the square root minus cosine t times this whole thing here, right? Okay, so sine cubed t cosine squared t. Oh, sorry, I have to get this one first, though, right? Yeah. 2 sine t squared t. Okay. And then minus this thing as well. So sine cubed t cosine t over this guy to the 3/2. So that's the numerator. All right, and the denominator is the square root of x prime squared. So that's going to be sine to the 4th divided by 1 plus sine squared t, and then plus y prime squared, which is cosine squared t. I think this simplifies. How's it going to go? We have to put this on a common denominator, right? So we'll have sine to the fourth plus cosine squared t plus sine squared t times cosine squared t over 1 plus sine squared t. Now, if you these two terms, you can pull out a common factor. Do you see that? Well, what's the common factor here between this term and that term?
Sine squared plus.
Right, sine squared t, right?
Yes.
So if you pull sine squared t out, what's left is sine squared t plus cosine squared t, which is 1. So this plus that is actually sine squared t. And sine squared t plus cosine squared t is 1. This whole numerator is 1. So it's 1 over square root of 1 plus sine squared t. And so we have to do the k numerator divided by kappa denominator to get kappa. So that'll help. We're going so the absolute value, I can just get rid of all the minus signs there and make everything positive. It'll be sine cubed t plus 2 sine t squared t plus sine cubed t cosine t divided by 1 plus sine squared t.
Professor?
Yeah?
I think this is the 3 over 2, right? Not 2, right? Denominator.
Yeah, down here it's to the 3 over 2.
No, kappa denominator. All to the 3 over 2, right? From here, from the equation.
Yeah, the square root of this guy.
No, all of it. You see from the equation there?
I mean, we're squaring x prime. So
Plus y prime, right?
y prime squared.
From the equation there in the screen.
Oh, to the 3 halves. Ah, thank you, sorry.
No problem.
So where are we then? This is to the 3 halves. And that means this is to the 3 halves. So is this. Thank you, Edmund. So that means we get a little more than just cancellation. That's completely gone. These two terms are multiplied by 1 plus sine squared t. And this last term comes as is, sine cubed t cosine t. And this is supposed to come out to sine t in the end. Okay, I don't want to spend a lifetime on this. But it comes out to sine t, 2 sine t. Okay, if I did it correctly, it would come out to 2 sine t. Anyway, that's how one would verify it. one has to not make any mistakes when you do this. And so that's how we know that this parametric curve, where is it now? We can verify that this parametric curve satisfies the requirement that curvature equals a constant times y. Now that might come as a little surprise. Normally you solve equations by solving. Here we guess the solution and verify that it works. Hard problems are solved that way. It's not always that you can solve for something. You have to wake up one morning with an educated guess, and you check whether it works, and it does. Okay, now a little more history. So, John Bernoulli is the younger brother of James, and I think those two compete. And John solved the catenary while James was working on the problem, and was very happy about that. And John has a son, Daniel Bernoulli, and Daniel Bernoulli took up the problem of the general elastica. But their approach is not mechanical equilibrium. Their approach is something called the calculus of variations. So here's how it goes. You're given 2 points, A and B, and you're also given 2 tangent directions, U and V. I can show you a little picture there. So this is the point A, this is the point B, this is the tangent direction U, and that's the tangent direction V. And then you want to also be given a length, L, for the curve, and you consider all curves that start at A with direction U, end at B with direction V, and have length L. Consider all possible curves. So in this slide, I've shown 3 of those curves, but there's infinitely many of them. And for each of those curves, you can calculate the potential. If it was a thin rod, what would be the potential energy stored in the rod? And we call that the bending energy. And there's a formula for it. You integrate along the length of the curve, and what you integrate is the curvature squared. And you have to do your integration with respect to arc length. So it's not with respect to t, not dt, but it's ds. Okay, so that's a little technical point there. So any curve, the goal is to find a curve that minimizes the bending energy. And it's thought that if you took an actual rod and, bent it so that it was at A and B, and then twisted it so that it had the direction U and direction V, then it would take the shape of an elastica. So it's a physical problem that they're solving. So the calculus of variations gave some equations, but Daniel Bernoulli, I think they were hopeless equations. They're 4th order, and he didn't feel like he could solve it. So he took the problem to Euler, and Euler was able to solve these equations. And so, Bernoulli is the one who set up the problem and, decided how to look at it. So Bernoulli also deserves a lot of credit. Quite often, half of the solution is setting the problem up the right way. So, okay, now, Euler has his equations, but these have been worked over a couple hundred years. And so the modern definition of elastica is this equation. So if you have a smooth parametric curve, and where the curvature, you have to work with the sine curvature. So you get rid of these absolute values, and it becomes the sine curvature. If it satisfies this differential equation, then it's called and Elastica. The C here is a constant. If C equals 0, this term is not there, then it's rectangular Elastica. Any other Elastica will have a non-zero constant there. And these are the figures that Euler drew to show his Elastica. There's quite a variety of shapes that you get from these Elastica. I think the reason he has all these points labeled is because he's had to calculate by hand the coordinates of these specific points. It's quite an amazing thing to do in 1750. And here's some other Elastica. I noticed that on this, you have this weight here, he shaded it. We don't do that anymore, do we? So you have to like that. Okay, now the draftsman spline. So now I'm going to start the second part of the talk. I should give a short quiz, right? Who is the eldest of the Bernoullis?
John what?
The eldest. James. John was the younger brother. How many Bernoullis are there in this tree of mathematicians?
4, right?
They're still going today. So I don't know how many, but yeah. So if you search, you'll find there's a Bernoulli in some university even today. Okay, so the draftsman spline, it's a drawing tool. And so we all have straight edges and we can make straight lines. But if you want to make a curve, but you don't want to do it freehand, then you could use a draftsman spline. And it's been used since the 17th century. And it's used quite often in those days for the hull of a ship, or even in airplanes they use it. Perhaps some of you have a father or an uncle or a grandfather who makes dowels. If so, he might have a draftsman spline that he uses. If so, I want to meet him. I want to see a physical draftsman spline. I've never seen one. Here's another picture. So on the left, they're designing the hull of a ship, and on the right, that's at Boeing Aircraft. I want to get a closer view of that first picture. And maybe we can zoom in a little bit. So the way it works, so it's a thin piece of wood, and it has a groove at the top where these little hooks lay into that groove, and they can slide in the groove left or right. And this weight here that's made of lead, it's called a whale or a duck. And that hook should be perpendicular to the curve. So that's when it's used properly. Now, here's the naive model of the draftsman spline. So you're given points in the plane. Need to have some points in the plane, I think. So P1, P2, P3, P4. And then one considers all possible curves that interpolate these points. Interpolate, yeah, I have it written there, right? A smooth curve that passes sequentially through the points is called an interpolating curve. So I'll draw an interpolating curve, but there are infinitely many. So the naive model is that the shape that the draftsman spline will take will be the interpolating curve with minimal bending energy. Do you all know what the word naive means?
Simple.
How's it?
Simple. Simplistic.
A little bit too simple.
No mathematics, only words, right?
No, it means, naive means there's a mistake in it because it's too simple.
Okay.
So,
Yes.
Okay, so here's the problem. The naive model is naive because there exist interpolating curves with arbitrarily small bending energy. And therefore, there does not exist an interpolating curve with minimal bending energy. It's hard to believe. How would you pass a curve through here with nearly zero bending energy? Hard to imagine. But it's possible. But it's in a way that you would never think of. So, okay, we have to do a little calculation. This one will be, I promise, we'll get this one all the way to the end. I have a circle. And the radius here is, let's say, r. What's the bending energy of this circle? Okay, so let's find our formula for the bending energy. There it is. Okay, so what's the curvature of a circle? Well, it's 1 over the radius of the oscillating circle. Okay, this is the oscillating circle of the circle. Okay, so the curvature is 1 over r by definition. And now we're going to integrate. So it's 1/2 the integral from 0 to L of 1 over r, a constant, ds. This is squared, right? What's the length of the circle? 2 pi r. Okay, so instead of length here, I can put 2 pi r. So we're going to get 1 over r squared, this constant, times 2 pi r. So it's the 2's cancel, it's pi divided by r. So the bending energy is pi divided by r. So if I make the circle really large, what happens to the bending energy? It gets very small, right? Yeah, so, okay, so here are the interpolation points. This one, that one, and that one. And now here's an interpolating curve that you never thought about. You make a big circle, or half a circle. And then you start on a new circle that has a slightly different radius so that it comes through this point. And then you come back here, and now you start at another circle with a slightly different radius. And you come here, and you keep going like that. And this point here, imagine it's not there, but it's out at Jupiter. Then the bending energy is very nearly zero, but not quite zero. And if you want it even smaller, you can go put it on a distant star, that point, and it'll be smaller. But you'll never get bending energy zero. So the minimum doesn't exist. The infimum is zero, but the minimum doesn't exist. So this was first observed at General Motors in 1964. So what was going on at General Motors is that they started to have digital computers that could control the milling of in their manufacturing system. And they needed curves that were described mathematically. And they had 4 people working on it. Garrett Birkhoff, Carl de Boer, Burchard and Thomas. Burchard and Thomas, I don't know them, but the first two are big names in mathematics. And so the way they modeled the draftsman spline is that they said that the bending energy will be locally minimal, okay? Meaning that if you have another curve which is nearby, another interpolating curve that is nearby, then the bending energy of the draftsman spline will be less or equal to the bending energy of the nearby curve. So here's a little illustration of that. So at the top, the curve there, that's say a draftsman spline, the curve taken by the draftsman spline. And then there's an envelope around that curve, and if you take any other interpolating curve, like this red one here, that stays in the envelope, then the bending energy of the red curve will be greater or equal to the bending energy of the purple one there. Okay, and they have some terminology for this. So a curve like this is called a stable nonlinear spline. The word spline was already in use with cubic splines. Cubic splines, maybe some of you have taken numerical analysis and you've seen a cubic spline. Cubic spline is a linear thing. You have to solve a system of linear equations to get it. But this spline, the draftsman spline, if it's going to minimize the bending energy, it's a nonlinear thing. So they call these nonlinear splines, or specifically a stable nonlinear spline. And in their reports, they mention, without proof, that if a stable nonlinear spline through the points exists, then each piece of the spline will be a segment of rectangular elastica. So when we talk about pieces, this one has 4 pieces. So from one point to the next, that's a piece. So that's going to be a segment of rectangular elastica. This will be a different segment of rectangular elastica, and so forth. So it's built with rectangular elastica. And so they actually didn't adopt that. They couldn't prove existence. It was too complicated. General Motors needs something this year, not 20 years from now. So that was the end of the story at General Motors, but researchers continued to work on it. And in 1973, Lee and Forsyth show that if a stable nonlinear spline through points P1, P2 to Pn exists, then, as I said before, well, see, now they're giving a proof that each piece is a segment of rectangular elastica. Also, number 2, the sine curvature is continuous. And 3, the curvature at the endpoints is 0. So when we say the sine curvature is continuous, what that means is that if you take any point like this one, coming in from the left, you're going to have a curvature, and coming in from the right, it's a different segment of rectangular elastica. It's possible it has a different curvature coming from the right. But they're saying, no, those 2 curvatures will be equal. And that happens at all the interior points. At the end points, the curvature will be 0.
So always they are symmetric?
Sorry?
So always they will be symmetric?
About the point?
Yeah.
The curvature will be symmetric, but the curve can be different. It's not exactly the same curve, but on both sides, but the curvature at the 2 endpoints, at the joining endpoints, will be the same. Okay, so let's call these 3 conditions the necessary conditions of Lee and Forsyth. And there's quite a lot of research where people look for curves that satisfy these necessary conditions. Do we all know the difference between necessary conditions and sufficient conditions? Okay, so if P then Q is true, it means that Q is a necessary condition for P. And P is a sufficient condition for Q. Maybe I can see that. So this is a sufficient condition for Q, and Q is a necessary condition for P. So a necessary condition for a stable nonlinear spline are these three conditions here. And in the literature, people find curves that satisfy these three conditions, but quite often they're unstable. I should tell you, the existence of these stable nonlinear splines is a big open question. It wasn't, it's by no means that they always exist. And people believe they exist, but proofs are missing. Now, the first existence proof, let's say the first general existence proof, was in 1978. This is in a technical report of Goulomb. It's an unpublished technical report. So that means it never went to referees to see if it's correct. And what they show, or what Goulomb shows, he's working with his student Jerome before they have a paper. And so he's building on that paper with his student Jerome in this technical report. The paper with Jerome has been published. So if you have a line and you put points on the line, we'll call them Q1, Q2, and so on, then there exists an epsilon positive, so that could be very small, and so small that I can't even draw it, but I have to draw something, so I'll put it big so you can see it. So the radius is always epsilon. And then in each of these little disks, you can choose P1 and P2, say, is over here. You can put P1, P2, P3, and so on, anywhere you want, in these small disks. And there will exist a stable nonlinear spline through those points. Will there exist a stable nonlinear spline through those points there? Who knows? It's not close to some points on a line, right? So it doesn't talk about this at all. It's a very special case. Now, there are about 40 papers in the literature on the topic, and that's the only technical report that proves some kind of existence, and nobody knew about it. One day, I was doing a search, and it just popped up on my screen. It was a photocopy of something that had been in the trunk of somebody's car for 40 years, and it was unreadable. But we managed to read it. But it has no citations. Nobody knows about it. So anyway, Albert Borberly and I, we got interested in the topic in 2010. And we've been working on that. And so from Quate University, there are now 4 papers on the subject.
And this is your son?
Yeah, the second paper is with my son. He started when he was 14 years old. He was my computer programmer. So we have a program called Curve Ensemble that we can look at these curves. So I'll give some ideas. First, I have to define an S-curve. Okay, so what's an S-curve? An S-curve is a smooth C2 curve that first turns monotonically at most 180 degrees in one direction, and then turns monotonically at most 180 degrees in the opposite directions. On the left, these are some examples of S-curves, And on the right, these are all not S curves. Well, why is that? Is this one not an S curve?
Because it's more than 180.
Right, it turns more than 180 degrees. Same problem with this one, right? The curve up above is more than 180 degrees. What's wrong with this one?
More than one direction, right?
Yeah, it has, I don't know, it's first going left, then right, and then going left again, right? So, yeah, so that's not an S curve. So, the significance of that is, so when Albert and I started, we had a fourth necessary condition. And it is that if a stable nonlinear spline through these points exists, then each piece will be an S curve. So, so what that meant is that instead of looking at all possible curves that go through these points, we can narrow our focus to curves that go interpolating curves where each piece is an S curve. And and then we took up this question again. Let me. This is the program curve ensemble. So, you have 2 points, and A and B, and then there's 2 directions, U and V, and then we ask whether there's, so we're looking at consider all possible S curves that connect in this fashion, and I should mention that the length is arbitrary. See, when Euler looked at this, the length was fixed. He had to look at all curves that connect, but with a fixed length L. But here, length is arbitrary, but we're saying that it has to be an S curve. And so we were able to prove that for any U and V, there are some restrictions, not every U and V, but for most U and V, there exists an S curve that has minimal bending energy, and you can see them here. So it turns out that if you look at this collection, so we have notation for it. Where is my chart? Beautiful A. A stands for admissibles. P1, P2 to Pn. So this is all interpolating curves where each piece is an S curve. And it has a curve with minimal bending energy. So it's not that it's locally minimal, it has a global minimizer. And we call that an elastic spline. Now, the purpose of this program curve ensemble was to see these elastic splines. So I hired my son to write this program. And once it was written, we could see the elastic splines. And we realized that there was something bad about them. And we had to make a restriction on chord angles. So if you're looking at an S curve, say like this angle here, this line segment from A to B is called a chord. And then there's an angle here that the curve makes with the chord, another one down here. Those are called the chord angles. And we're saying that we don't want to allow the chord angles to be greater than 90 degrees. If you do, then there's something bad about elastic splines. So if you had something like this, so if the curve started off like that, then this is more than 90 degrees. We don't want that. We disallow that. So with that setup, now in the second paper with Albert, we put a pi over 2 here. And now it's the set of all interpolating curves where each piece is an S-curve and the chord angles are no more than pi over 2. And so this also has a curve with minimal bending energy. And we call those restricted elastic splines. But here's the big question. Are restricted elastic splines nonlinear splines, stable nonlinear splines? Because the original problem was existence of stable nonlinear splines. The answer is sometimes. And here's the big theorem that was finally accepted for publication last month. So you're given some points, P1 to Pn. We have to define stencil angles. So here are the points, P1, P2, P3, P4, P5, P6. These little red angles are called stencil angles. And then there's a critical angle psi, which is 37 degrees. It comes up like this. This is rectangular elastica. So there's a unique point where it makes a 90-degree angle there, and then this is psi. So if all the stencil angles are less than psi, then the restricted elastic spline will be a stable nonlinear spline. So existence of stable nonlinear splines is now proved, provided all the stencil angles are less than this 37 degrees. And we've also been able to prove that this critical angle psi is sharp. So if you, instead of psi, you use psi plus epsilon, then the restricted elastic spline will not be a stable nonlinear spline. So I thank you for your attention. I'll stop.